welcome back. In this video, we're gonna go through another application of differentiation. It's called the mean value theorem. The mean value theorem is not too different from the Rolle's theorem. It's another version, in fact, of the Rolle's theorem. Rolle's theorem is the special case of the mean value theorem. Here is the description of the mean value theorem. So let's just read it out. So we have a continuous f on the closed interval a and b, and differentiable on the open interval a and b. And the mean value theorem guarantees the existence of a number c in between the endpoints such that, so f of b minus f of a divided by b minus a, well, we recognize this from somewhere. In fact, this is the slope of the secant line connecting the points f of a and f of b. Okay? So remember, in the Rolle's theorem statement, we had f of a exactly equal to f of b, because this was one of the conditions in the statement of the Rolle's theorem. In fact, if they're equal, then this becomes 0, and then f prime c is 0. So in the mean value theorem, this doesn't need to be 0. So this could be totally different from 0. So the secant line doesn't need to be horizontal. And whatever the slope that the secant line has can be achieved at an interior point C. So that's why I said, like, the mean value theorem is the most general case, and the Rolle's theorem is a special case of that, where we are trying to look for a horizontal tangent line. We're given two functions. One is sine x on the closed interval 0 and pi, and the other one is e to the negative 3x on the interval 0 and 2. So let's start with part A. So before we look at the conclusion of the theorem, we first want to verify that f is continuous on the closed interval 0 and pi, and as well differentiable on the open interval 0 and pi. But the good news is that sine x is one of the functions that we worked out in the previous chapter for continuity and differentiability. And this function is continuous and differentiable over the real axis. So not only on this interval, but everywhere on the real axis. In other words, it's differentiable and continuous on the interval negative infinity and infinity. So in particular, interval 0 and pi. So we can go ahead and check this, since we have the continuity and differentiability already satisfied for sine x. So what is f prime first? Let's just find that out. Well, you can use the differentiation table, the formula card for this. So the derivative of sine is just cosine. All right, that's good. So then on the left-hand side, you have cosine c equal to f of b, which is sine pi, minus sine a, which is in fact 0, because b is pi and then a is 0 here, and then all divided by pi minus. So at this moment, go ahead and use your TI-84, but don't forget to put it in the radian mode and calculate sine pi minus sine 0 divided by pi minus 0. And you will see that since sine pi and sine 0, they are both zeros. Okay, so this turns out to be 0. So this is almost now like the Rolle's theorem, because sine pi and sine 0 are both 0, because they're the same values. So we're looking for a horizontal tangent line at an interior point for the interval 0 and pi. So essentially, we are trying to solve cosine c equals 0. All right, for this purpose, you can use the unit circle, or you can use your calculator. When you use your calculator, you're going to be cautious, because here c is cosine inverse of 0. And if you punch this into your calculator, there's going to be only one value popping out of this. But we have more points, in fact, for which, or more c values for which cosine is 0. And how do you find them? You're just going to add integer multiples of pi to pi over 2. So n here is an integer. All right, in particular, we're looking for c's fitting in this interval, so 0 pi. So for n equals 0, we have pi over 2 here. That's a good candidate. So I'm going to take c equals pi over 2. And for n equals 1, it's going to be pi over 2 plus pi. That's 3 pi over 2, which is not in that interval. So it's a good practice for you. Check other n values, then convince yourself that pi over 2 is the only candidate that is in the interval 0 and pi. So what that means is that when we look at the graph of the sine function, we should have a horizontal tangent line at this point. And here is the graphical outlook of the function sine x over the interval 0 and pi. And if you look at the secant line connecting f of 0 and f of pi, you can see that it's a horizontal line. And the same horizontal line can be achieved as a tangent line at the point pi over 2. As you see, there's a flat horizontal tangent line at pi over 2. And in fact, this is what is guaranteed in the conclusion of the mean value theorem. So this graph, in fact, confirms the conclusion of the mean value theorem. All right, for part B, we're going to follow the same process, but this time the function is e to the minus 3x. And we know from the previous chapter that exponential functions are always continuous and differentiable over the whole real axis. So we had no problem to violate the continuity and differentiability, in particular on the interval 0 and 2. So all two conditions of the mean value theorem are satisfied. So all we're going to do is just to check this equality here for this f. But first we need f prime. You can use the chain rule for that. So the outer function is the exponential function. So essentially the derivative of that is just itself. But we have to multiply this by the derivative of the exponent, which is negative 3. And now we can go ahead and write down this equality here. So negative 3 e to the minus 3c is equal to f of b, which is f of negative 3 times 0, right? Negative 3 times 0, and minus e to the negative 3 times 2, all divided by 2 minus 0. All right? And in short, this is equal to negative 3. This is equal to 1 minus e to the negative 6 over 2. So in short, this equality is reduced to this one. So now we are supposed to solve this equality for c. So why don't we divide each side by negative 3 so that we get rid of this coefficient here. So that this equality is reduced to this one. This is something we have done in pre-calculus sections, like solving an exponential equation. Once we leave the exponential term alone, then we take the ln of both sides. So essentially we put an ln here, but the left-hand side now turns out to be just the exponent. So it's negative 3c equals ln of 1 minus e to the minus 6 divided by negative 6. So it turns out that negative 3c equals the ln of this. I can go ahead and divide both sides by negative 3 to find c. And here is the c value. And this is the only c value that pops out of this equality. And you can go ahead and punch this into your calculator. And that's good news because this point is in fact in the interval 0 and 2. And here is the graphical outlook, e to the minus 3x graphed on the interval 0 and 2, as you see, 0 and 2. And if you connect the function values at the endpoints by a line, so that is in fact our secant line. As you see, I have a tangent line at this point, which is parallel to the secant line. So this graph, in fact, confirms the conclusion of the mean value theorem. And this ends the video, and thanks for watching. I'll see you in another video. Bye.